Alright, so things didn't work out in class very well today, so I was just going to try this at home to test out the technology. We'll just go through this kind of quickly and see the things that we talked about in the class today. So starting out, our purpose of the class is to look at making ideas into products, and specifically the metal part of products, or using metal to make the products that we're going to be making. So there are all kinds of things that we might want to make, cars or cars of the future or cars of the past. And we'll talk about how might you produce the things that would be used to make that kind of vehicle. Planes, certainly. All of these items are mostly polymeric, but they require a lot of metal in the process of making them. The last for making soccer balls, or the lights that are in some of the classrooms. How do you make pencils? How do you form the graphite that is inside? How do you cut the wood to the right size for the outside, join the whole thing together? Sometimes you need very specific surface finishes, like in a replacement hip, as is shown here, so that the bone can grow into the matrix afterwards. Sometimes you have super high precision, so the tolerances on an aircraft carrier are absolutely phenomenal. It's something like a 1/4 inch from end to end. How do you do that? How do you go about that? What are considerations that you have to have in the process? It turns out that the precision of an aircraft carrier is similar to the precision of a mechanical watch. And so how would you go about making these very small gears and having the accuracy in all of those parts that is required? That's been done for a long time with a craftsman. How could you do it in a more automated manner and make it more financially feasible? Anyway, I think a useful question is to ask, why do PME students need to know about the metal manufacturing processes? And in class today, students talked about the fact that many of the polymeric processes require metal. So whether that be the extrusion screw, or the injection screw, or the barrel, or an injection mold, some tooling. Also was noted that even if there's something that you can do, like milling parts with metal, you can also mill polymers, you can mill things, mill composites as well. And so a lot of the understandings that we'll gain will go back and forth between the different categories. So we're going to have 5 big ideas in this class. The first big idea is going to be reshaping material. So we're going to start there. That's either mushing the metal into shape, or maybe melting it and turning it into the right shape that way. The second big idea is going to be the subtractive processes. These are what we often think of for the metal machine shop. So things like mills and lathes, bandsaws, drills, all of those kinds of processes that remove portions of the material in the form of chips to make what you want. Grinding is also in this category. The third is addition processes, so that can be additive manufacturing, but also the non-chip forming processes. So there is a group, they are often called the non-traditional processes, but that's not such a good name because they're used all the time. Non-chip forming is a little bit better name for them. They have some strengths and some weaknesses. They tend to be slow, they tend to be inefficient as far as the quantity of energy that they use to make them happen. They tend to be slower, but they have some amazing capabilities, and we'll find that out when we get there, what those capabilities are. And then the last thing is joining an assembly, so taking 2 pieces that are formed and putting them together. This could include bolting and riveting, but we're mostly going to focus on welding. It could also include adhesives. And then underlying all of these is metrology or measurement. We have to, at all of these steps, be able to measure the part to know if we're making the right part. So the things that we're going to study in each of those, or some of the things that we're going to study in the reshaping, we're going to look at casting, and we will actually go and create casting molds and then go over to the art department and do the casting. We can also form things, forge them, have dies slamming together to form it into the right shape. We can shear it, punch it, roll it. Sounds very violent. A lot of it is. The second is that we can use subtractive processes, and so we're going to spend a fair amount of time here because they're sort of the most common. And so milling, turning, drilling, cutting, grinding, etching, as I had said before. And so these are more familiar, but very, very heavily used. Then we have addition, and so additive is a possibility. In here we're also going to talk about some of the non-chip forming like thermal spray, electrodischarge machining, plasma arc, things like that. And then finally in the four big ideas that are stepwise, we'll talk about joining things together, and as I said, we're mostly going to work on welding in that category just because of time. And then we have metrology, measurement underneath the whole thing. How do we measure the parts? How do we measure the effects that we've made as we create these parts? Things that we'll learn. We'll learn how does the process work, sort of what are the basics of the process. We'll also learn why would I choose this process. One of the things that we'll find is that every process affects the properties of the part that we're trying to make, and the properties of the part that we're trying to make affect our choice of processes, and so it goes back and forth. The nice thing is that in metals there's a giant reset button. Not always available, but often we can use heat and time to recover the properties that we wanted at the beginning. And so we're going to think about that. When would we choose this process? We're also going to talk some about how we calculate the important process parameters. In this class, we're actually going to do almost no calculations, very, very few. But we are going to use equations a lot and graphs. And the reason that we're not using a lot of equations is that the equations that you can do simply in a class sort of time are so simplistic as to not be very helpful numerically. But the equations are helpful because the equations give us order of magnitudes of understanding. What is the most important process parameter? How much does it affect different outcomes of the process? Some things will be a linear input, some things will be an exponential input, and so that's the kind of thing that we need to know, and we'll look at equations to understand that kind of thing. What are the important considerations when using this process? Every positive process has some negative outcomes, and so there will be some unwanted outcomes, and we'll need to know when that is okay and when that is something that we have to take care of and when it's a non-starter. And then we'll look at how would my design change in order to optimize this process. So just like if you decide to injection mold a plastic part, that affects your design. You're going to have draft on the walls. You have a different amount of draft on an interior wall than an exterior wall. It's going to affect the wall thickness everywhere. You're going to try to keep very uniform wall thickness so that the plastic flows evenly through the part. You would always go from thick to thin. You never go from thin to thick because the molecules will expand out and you get very different material properties in that area. So there are just a whole bunch of considerations that you have in that case. Similarly, if you're thinking about designing something for a metal manufacturing process, understanding the process that you're going to use would change the design characteristics of the part. And we'll talk about some of those. Okay, why are we learning this? Well, there's a little bit of bad news. The bad news is that at the end of the course you won't be a master machinist, you won't be a manufacturing engineer. We will not have utilized all of the processes that we discussed. We just don't have all of them. There is good news though. You will have created an assembly using many of the processes, especially the common ones. We'll gain an understanding of what it takes to manufacture parts. That's really important because as a polymer engineer, you may be needing to get a new injection screw, and so you need it to have the right material properties, you need to have the right tolerances on the part, and that will help you to choose the right process, to know what could create a part that has the right material properties and tolerances, and then also know what to look out for. And it would change your design because you can sort of look at where are the cost trade-offs, where I can save some money, or where do I need tight tolerances, that kind of thing. You will have learned about tolerances and have a feel for how hard or easy it is to achieve those, and you'll be able to speak machinist, which is really helpful when you go into a shop and ask for something. One of the classic confusions is that many engineers would talk about 1/10 of an inch and think that they're talking about 0.1 inches. But if you're talking to a machinist who machines in inches, then 1/10 of an inch is 1/10,000th of an inch. It is 0.0001 inches. So you're expecting something to be really easy and inexpensive. And when you talk about 1/10, the machinist is talking about something that is relatively difficult and requires a lot of skill and care. That's scare. Anyway, and so it's going to be pretty expensive to achieve that. So anyway, we will be able to speak machinist, and we won't act like a goof in a shop environment. So there we go, certified not a goof. We're going to skip that and talk about a few things in the syllabus. The office hours are 4 to 5 on Monday and Friday, but the word is if the door of my office is open, and that's ET144 where you came and visited. If the door is open, then I am in the building, and if the lights are on, then I'm either in my office or I'm close by my office. You might check the manufacturing lab because I'm doing a lot in there. We don't have a manufacturing technician right now, so I have a lot of work to do in there getting ready for labs and a lot of different classes. The lab is in ET136. It's essentially across the hallway from where from my office and down just a little bit. For you, it would just be the lab days. If you're feeling ill on a lab day, don't come. Send me an email telling me that you're not feeling well and won't be there, and we'll work out a way to get the lab done. Maybe you'll come to a different section, or maybe we'll set up a time for you to come outside of the normal labs. What happens if you miss a class? Well, you're not going to miss a class, but anyway, it will be very important to watch the videos ahead of the classes, because in the classes I will assume that the video has been watched. You'll see that the videos are due, video questions and answers are due at 8 a.m. on the day of class, so you'll need to try to comply with that, and then I'll use that to be able to check and see where the understanding is. The midterm is on Halloween. Sorry about that. That's the way it came out though, and as we discussed, it can happen anytime during the day. What day are we casting metal? I think it's on the 22nd of October, and so if you're able to come that day, we can see, especially in the second half of the class. That would be great if you could come for that, and we'll be over at the Art Annex building for that. Before class each day, the videos are due, and then there are 3 date errors on the tentative schedule. There's something right after Thanksgiving that is listed as December, but it should be November for 2 of the dates, and then 1 of the dates doesn't have a slash in it. This is all things that we've talked about. There is no textbook required for labs, so you need to have closed-toed shoes, long pants, and safety glasses. The safety glasses need to have Z87 or Z87.1 or Z87 Plus. There are a number of different markings, but that is the ANSI impact resistance of those safety glasses. That needs to be marked on them. Sometimes students ask if they can wear their chemistry goggles. Most goggles do not have this impact resistance. If they do have it, you could wear them, but it's not really a very good choice. Safety glasses are relatively inexpensive, They're sort of $1 or $2 if you don't wear glasses, and up to $10 if you do wear glasses. And I know they're a little bit of a pain, but they're well worth it for keeping things out of your eyes. The other thing is dial calipers, so we'll talk about those in just a minute. I would really like you to have dial calipers. If you would like to talk about it, the lab can be done with digital calipers, but it is better with dial. And the reason for that is that the calipers, dial calipers, you can see more of what's going on, and so you can tell when you're getting a good measurement. There are lots of ways to measure something incorrectly, only one way to get the correct answer. And until you have a really good feel for it, the dial calipers help you get there better. Some of the labs will happen outdoors. I'll try to give you warning on that, so you can bring a jacket just because it's a little cooler. Here's a set of calipers. Thing that you need to look for really carefully on them is right here. This is the resolution. So that is between two of these lines on the face of the caliper. What is the distance that one of those lines represents? And on this set of calipers, it is 1/1000th of an inch, 0.001, and your calipers need to have that resolution. This is a very common capability of machine tools to be able to hit 1/1000th of an inch. Just for scale, that is about between 1/3 and 1/4 of the thickness of a sheet of paper. So it's relatively small, but common machine tools can get this done relatively easily, and that's why we need to be able to measure to that level. If you get your calipers at a machining kind of location or on Amazon, most of them will have this sort of value. If you go to a place like Hardware Sales, you have to be really careful. Some of theirs will be in fractions. Those are not nearly good enough. And then some of them will be 0.01. That's a woodworking caliper. It is not an engineering caliper, so you need to get one that has higher resolution than that. This is the breakdown of the grades in the class. Only thing to say here, I will give you some help on understanding what's going to be on the midterm. Final exam is a little more than I would like it to be, but anyway, that's where we are this year. And then there is a point for a group presentation, and as we said, I'll have you write up a portion of that presentation. Just create it, and you won't have to give that. Get your work done on time, maximum score of 85% if it's turned in late, and then it has to be submitted within a week of the original due date. So there we go. On the syllabus, it has the labs that we will be doing. It also has the video that is due. This video, 2A, 2B, is due before class on Tuesday. So this is, it's on Canvas, but anyway, it is due early on Tuesday morning at 8 o'clock. There is a midterm on October 31st. The presentations will be on the 17th and 18th. I don't know exactly how we'll do those for you, but I have old presentations of all of the different topics, and so I can give those to you. And then the final exam is currently scheduled for this time. We'll have to see if that overlaps with the time that you have for the other exam, and we'll work out something. Casting pour is the day that we won't be in class. Doesn't matter to you as much because you won't be there. We talked about an inclusive and diverse learning environment in class, and some things that we talked about that are going to be really important are being supportive in the lab, helping each other. We all have different experiences, and there are things that we may be scared of or things that we may have confidence in. If you have confidence in a process, it's great to help other people, but the way to help is to stand there and help to explain how it might be done, help the person, or just help by answering questions that they have, but don't push someone out of the way and take over. That doesn't help anybody at all and doesn't really get it done. We also just want to be careful. If we see something that is not safe that somebody is doing, we will point it out, and the reason that we'll point it out is because we want everybody to be safe and go home safely, and so we're going to point that out, and it isn't going to affect anybody's grade. It isn't to embarrass anybody. It's just to say, hey, I care about you. I don't want you to get hurt this way. So I would like to just point out that from an outside perspective, this doesn't look very safe. We talked about what is safety and decided that safety is an attitude or a set of processes and plans that we put in place to help us help us and others to not get injured, and also to protect equipment, but primarily people first. And it can be something that we don't do, but it also can be something that we do ahead of time to make it safer. So we can do proactive things to be safe. And we talked about some downsides to safety. They can, things like PPE can certainly get in the way and make it harder to do the work that you want to do. But it will keep us safer in the end. If our PPE is so onerous that it is causing it to be less safe, then we need to consider how we might go about it. And then the final question here, what would we do for some good safety practices around a lab full of big machines with razor sharp spinny bits? As I said, closed-toed shoes, long pants are critical to have. Not having drapey clothes that will get caught in things is pretty important. Not having hair that's out that's going to get sucked into something is important. We will mostly be working on machines that have guarding on them, and so this is a little bit easier to act around those safely. Safety glasses are really important in the lab. And then just having a good practice of following the rules. We'll discuss that more when we get to lab as well. How do we do well in this class? Watch the videos before the class and do the homework so that you have the basis for the class. Do the class video every day. Take notes. There are slides that don't say everything. There will be a slide that just has a picture of a graph, and we'll talk about it for a while and what it means, but it would be important to take notes about it. It's going to be harder for you to participate in the group discussions. We'll see how much of the group discussions I record. We'll just have to see how useful that is. Try to learn a lot in lab, ask questions, try new things. These labs are pretty low stress, and so there is not a big lab report that's due. There's not a certain amount that has to get done, but I want you to try things and I want you to figure things out as you go through them. And so it's an opportunity to learn. It's not a high stress kind of environment. Ask lots of questions, and then come by my office or email me questions, especially since you're kind of out of sync with the rest of the class. That would be great. Take an active role in the group project, which will be done, and begin studying for tests early so that you can come and ask questions before we get to the test. Just a little bit about me and why I like doing manufacturing. So I started out, after I got my master's degree, started out at Caterpillar with these big engines, and I built these connecting rods. So the connecting rod is the part that goes between the crankshaft, that's the roundy round part, and the piston, which is the up and down part where the power is put in by the explosions that are happening. And so this connecting rod is sort of the length of your arm or a little bit longer, well, your lower arm, and it weighs 35 pounds or so. Is the most highly stressed member of these engines, because when these engines were originally designed, they were producing half the horsepower that they are today, and the connecting rod has not been allowed to grow any bigger because of the space that it has inside the engine to be in there, and a couple of design constraints that they have put on this engine for its entire life. So I got to do a lot of really cool things when I was there. The joint right here between the cap, which is this part, and the rod, which is the rest of it, is a really critical joint, and if it has any extra space in there at all, it will work itself to death as this cycles over and over and over. It's also a pretty hard thing to create because the cap is a little bit flexy, so when you put it in a fixture and spin it up to speed to create this joint, it will actually open up. So while I was there, I got to do a lot of work. I was the manufacturing engineer for the production line for these connecting rods. And I got to buy a lot of machine tools because we took a cell that was really dangerous and very hard on people's bodies because of just having to lean way over and lift these rods over and over and over. People couldn't work in the cell for very long before their body would just kind of give out and they would have to go work somewhere else in the plant. And so we were able to put in these machine tools. We ended up not eliminating any jobs, but we took it from a job that somebody could only do for a few years before they started to suffer physical effects and made it into something where the same person was then making sure that the machine tools, the robots, were doing what they were supposed to, and they were loading tools and watching the production and making little tweaks to the production to get a better part overall. But a really neat process. So I went there thinking I was going to do design, but ended up in manufacturing, and I loved it. And so that was the start of manufacturing, and I stayed in manufacturing. After my PhD, I went and worked with very high precision machine tools and made little tiny lenses like this. It's hard to tell. The little circles that are here are not the lens. The lens is in the very middle of that. It's about 200 microns across, so it is the diameter, 2 hair diameters, and it is a very complex shape. It's not just a little hemispherical. It's got a lot of little wiggles in it to direct the light just right. And super tight tolerances. These lenses over here and these 2 prisms had to line up with the 2 lenses over here when you put them back to back to an extremely tight tolerance. And so I had to make a fixed ring system that would move this thing across the face of this machine tool to be able to create each of these little lenslets at the center of rotation and have them all so that every lenslet was within 1/100th the diameter of a hair in X, Y, and Z from any other lenslet on the whole thing. So a really neat project. About $60,000 to create the first one. They got a lot cheaper after that, but just developing that process. I also there worked on giant optics. So how do you take big billboard sized mirrors that are all individually shaped to focus the light at a certain point? This is a tower that's 200 feet tall, and all these mirrors are out in the field and they focus the light. You can see it's focused here in space, and it is so hot that it's creating plasma right there just out in the middle of the air, not hitting anything. And so we would use this to collect the heat energy of light and then use that heat energy. You can store that and then use that to create electricity later on. I created this molten salt test loop while I was there. These are people just for scale, but it had I don't know, 10,000 gallons of molten salt in it that we could flow through the pipes at 1200 degrees Fahrenheit, 600 gallons per minute, and 600 psi. And we could take test subjects that people built that they wanted to run molten salt through, and we could mount them on the ends of each of these and then flow molten salt through it so that they could test those either for collecting energy or for operating back and forth, all kinds of things like that. And this is a huge design challenge because you have a point right here, a giant tank in the ground with 10,000 gallons in it, and you have a test fixture right here. So that's 2 fixed points, and when you heated up this piping from the temperature where you created it to 1200 Fahrenheit, it would grow by more than a foot. And so you have to do something to take up all of that expansion in the process and not tear up all the welds that are in this. So how do you do a weld in these things that will be able to take on that kind of motion and that kind of expansion and not just come apart? It cannot leak, because if the molten salt leaks, it ruins the system that it's in and then freezes up, and it's nearly impossible to get off. And so you have to build this thing and know that it's right before you ever put salt in it. So that's pretty challenging. All kinds of neat challenges that I did with that. Alright, wanted to quickly talk about the Canvas site for just a minute to point out some things that might be helpful on the Canvas site. Of course, there are the different assignments that you have here. But along with those different assignments, there is a couple of pages, and you can get to those pages either on these links right here, or you can go to the pages link over on the side. On the syllabus and administration page right now, the syllabus is there if you want a copy of the syllabus. And then there's also classroom and video PowerPoint slides, and these will be uploaded to this site. You can see that it contains all of the old ones from previous times, but then as we go through them, I will upload the new ones. So here you can see the presentation from today is uploaded, and that will have notes in it. When I ask questions on the slides, the notes will be in there about the answers to those questions. Other things that are on these pages that you might be interested in later on, there will be study guides. There aren't any yet because we're not that close to a test. And then that's probably what we need to know right now, the things that are most important. So anyway, I will post this, and hopefully this will work out for you and we'll get things to work better in class next time. All right, thanks.